Hi folks. Now that we've talked about sort of the foundational tests that involve stress and strain, especially the universal testing machine, sort of the basic components of our tension and our compression and our shear and our torsion and our flexure, I think I named all of them correctly, that we do inside of the laboratory, there are other places where we need to test even more facets of our materials. Of course, as we've been stating all along in the class, whenever you make something and make something new using existing materials or even inventing a new material and making something new out of it, we have to make sure that it is, one, safe to use, and two, make sure that it stays together once your customers get a hold of it. We don't want it to fall apart or break. One, again, for safety issues, lawsuit issues. The second one is we don't want to have these products that we make come back all the time and have to issue new ones. So we most definitely want to make sure that they stay put together once we put them together. So there's all kinds of additional testing that we can do and we need to do in addition to the basics of using the universal testing machine. And that's what we're going to look at now and see some of the different ways of doing things. Let me push a few buttons here. Let me switch out of this and get back over to our Prezi. So one of the first things we can do is we talked about flexing and compressing and stretching and tension and twisting the entire object. But sometimes the device we're looking for, we just want to test just the surface, see how scratch resistant it is, see how resistant it is to puncture and the like. So you can see here that there's an entire area of testing called surface hardness testing. And like I mentioned before, we want to measure resistance to surface penetration and indentation, meaning if you put something on it or something sharp or even blunt drops on it, will it make a dent or will it make a scratch? And there are different ways of doing this. They're usually named after the person or the engineer or the scientist who developed a particular test, and then other people started using it. So then they went ahead and gave it the name, named the test of the person who invented it. So we're just going to go through a real quick sort of tour of these things first. Not so much that we can memorize these things, but if we do see them inside YouTube videos or when we're studying other materials throughout the course, where they say, oh, by the way, this brand new metal or this brand new steel alloy happens to have a Brinell hardness number or a BHN of blah, 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 we know what they're talking about. So what you can see here is the Brinell test, named after the scientist Brinell, engineer Brinell. Simply what they do is they take a very hard ball, very similar to the little ball that you would find inside a pinball machine. It has a certain dimensions. The ball itself, you can see it has it's measured a particular diameter of the ball itself. They go ahead and place that on top of the material and then stick the whole kit and caboodle into the UTM and compress it. So imagine, if you will, we were compressing the chalk. This time around, we can take a big piece of chalk and we can take this little Brinell little ball and then put that on top of the sample and then squish them and see how much of a dent it makes. So you can see here that we can measure the depression that this makes, what the diameter of the depression is. Obviously, if the ball goes the whole way through, then the diameter of the depression equals the diameter of the ball. Just like, dropping a ball into a pile of cottage cheese, it would just float through or sink through. In this case, if it doesn't go the whole way through, we get some sort of ratio between what the diameter of the ball and the diameter of the impression is. A different surface type test, obviously not a ball anymore, not a nice smooth surface, but a very pointed surface. It's called the Rockwell test. And again, we're just going through these names so that we know what they are when they get used later on by some of our materials videos. You'll notice here that the Rockwell test uses a pointed hard object. In this case, this Rockwell point happens to look like a nice triangle. Some of them are pyramids, pyramidal. And they go ahead, again, it's a compression test. They just put this this little pointy object in between the compression platens. Go ahead and do the UTM test, and then come back and see how deep this particular indenter sinks into the material itself. So here we go, various Rockwell scales. You'll notice that the indenter in this case happens to be a diamond. Diamond is pretty hard. We'll be learning about diamonds later on. It's one of the hardest naturally occurring materials. Over here, this is the use. This is what they're testing. Tungsten carbide happens to be an alloy. We'll be talking about metals and alloys coming up. Aluminum, brass, and steel are alloys, and then so are harder steel. Steel is an alloy. We'll be talking about that. You can see how they have different various type of indenters, various type of abbreviations for the indenters, and then different scale names. So nothing to be memorized or worried about, just to know that, oh, by the way, they have an indention test called the Rockwell test. Not to be outdone, we have the Vickers test. The Vickers test happens to use a diamond-shaped indenter, so it's called the diamond pyramid hardness, or DPH. Not so much that the material itself is made out of diamond, I guess it could be, it's just that it happens to have a diamond shape. So instead of being round, like our Brinell test, this has a pointy diamond space, or a pyramid shape. And again, we test how deeply this squishes into the surface of the sample, and we get a DPH test for the Vickers test. Oh my gosh, in addition to the diamond hardness tester, we also have the Knoop test. In this case, the Knoop tester was not an equilateral pyramid. It's a pyramid or a four-pointed, sort of a kite shape or a diamond shape that's not symmetric, that has a different width, as you can see, and a different height. And you go ahead and you measure the width and the height ratio, and you get the KH and the Knoop hardness number. Again, we're just running through all these things. You can imagine that back in the day, different manufacturers and different people who were using different materials just simply needed to know, hey, what material should we use for this product, and which material is better at not getting dented. So they had to invent their own way of measuring these things. So all these named tests happen to be different ways that different labs around the country and different labs around the world measured this, and then now in 2015 they all show up in a Wikipedia article somewhere on different ways to measure hardness. So we have the Knoop hardness measure as well.